How you doing? Going to have a little look at 2018, the higher level question, the hydrostatics question, question 9. There's two parts to this. The first one's to do with a hollow sphere floating, and we're looking to find out what volume of the buoy is immersed. They give us the density and they give us the dimensions of the sphere. The second one is regarding an inclined rod, and we'll deal with that in a moment. Let's have a little look at this scenario. So here we have a hollow sphere, or my representation of it, and so we've all this metal that's making up the sphere, but that's only this bit. So why is the sphere floating? It's floating because all the forces are equal at this point, and there's two main forces, and that's the forces up and down. And the force up in this case is buoyancy. Most cases of a body floating, it is buoyancy, and the force down is weight. There is only two forces in this case, and so it's quite simple for us to say that the force is up equal to force is down, so the buoyancy is equal to the weight. So what is buoyancy? Buoyancy is the density of the liquid times the volume of the liquid displaced times gravity, whereas weight is mass by gravity. Mass by gravity, in this case, mass of the object, we'll say, is equal to the density of the object times the volume of the object times g. In this case, we have a little bit of a different scenario because we've got two volumes. We've got the volume of this outer sphere, and then we get this volume of this inner sphere. So the volume of the inner sphere is all made of air. That adds no mass to it. And the volume of the outer sphere is actually equal to the volume of the total outside sphere minus the inner sphere of air, and that gives us this metal bit here. Okay, so if I just look at this, the density of the liquid is 1,000. The volume of the liquid displaced is more or less what we're looking for. G is equal to the density of the material was 3,440 times G, now times the volume of the sphere. So the volume of the sphere formula is 4 over 3 pi r squared, which is 0.7 squared, and then minus 4/3 pi times 0.65 squared, cubed. So let's just figure out what those volumes are. You'll see instantly the g's cancel, and we just turn this down to 3.43 times 4 divided by 3 and 4 divided by 3 times pi times 0.7 cubed. I'll get that right this time. And that's 1.437 minus 4 over 3 times pi times 0.65 cubed. 4 divided by 3 times pi times 0.65 cubed minus 1.15, so plus 1.437. So that's that, multiply that by 3.43, and we say that the volume of the liquid displaced is equal to 0.98. We dealt with everything cubic, kilograms, meters, and meters square cubed, so therefore it's 0.98 meters cubed. Is that the answer? That's the volume of the liquid displaced. When we go back to the question, it says what percentage of the volume of the buoy is immersed. So percentage, we need to find out the total volume of the sphere, and that is here 1.437
Therefore the percentage is equal to the volume of the liquid displaced divided by the volume total. That's equal to 0.98 divided by 1.437. Multiply that by 100. Comes out to be 69%. Okay. Hey, so this is the 2018 question 9, second part B. It was worth 30 marks. So this is the scenario that they give us, that a rod of length 2h is suspended at height h above water. The lower end is in the water. It makes an angle of 45 degrees with it. The question here is to find the specific gravity of the object, and that's the rod. So that's what we're trying to do. So there's a tension force up here, there's a weight force here, and there's a buoyancy force here, and those forces all add up to each other to equal. That's the forces up equal the forces down. You can figure that out, but we don't really need that because we don't have anything about the tension, and so it's probably better to solve it using the other method, which is the equilibrium of moments. So the moments clockwise are equal to the moments anti-clockwise, and that's fine. I suppose it's trying to put in the forces really. So if I'm right, pretty much close to this anyway. There's a weight force that's going down. This weight force is created by the density of the object, the volume of the object, and gravity. It operates from a distance that's h down the rod, because that's halfway. However, when we find the moment of something, which is forced by moments being forced by perpendicular distance to perpendicular distance, but that's to the line of the force. So you might have seen me just kind of sketch a bit up here. So this is the weight, the line of the weight force, and this is the perpendicular distance between the action of the weight and the perpendicular force. So this is actually the side we're trying to find. So we're going to do some trig to do that, but it will work out a bit okay in a bit. So here's the line of the water, just up here. So there's a buoyancy force, and again the buoyancy force operates from halfway through this submerged part of the rod, and that's a buoyancy force, and that's working upwards. We give that as B, and we say that B is equal to the density of the liquid times the volume of the liquid displaced, so we'll talk about that in a second, times G. So the volume of the liquid displaced is like, what is volume? So volume of a rod, so we can assume that this is a uniform rod. The volume of a cylinder is pi r squared h. You should know that. The pi r squared is just the area. So it's area by h, the length, if you like, height, whatever. And you'll see that there's a volume of the object here, which is the rod, and a volume of the liquid displaced, which is also the rod. So you should notice that the area is going to be overcome. Okay, so that's not the crucial bit. We need to find out the volume of this is, and this is this h here is this distance here. We often call it x in these problems, but that's what we're looking for here. Okay, so we're going to need x as well for different for the other reason that the moments is anti-clockwise will be the buoyancy by the perpendicular distance, and that is going to be trying to resolve this distance here. Okay, sorry, apologies, this distance here, all the way to the x. So we're going to have to make a few decisions and stuff on this. Okay, so this isn't a difficult problem, except for there's quite a lot of trig in this, and it can get a little bit messy quite quickly. So I'm going to just choose to redraw the diagram. So just here I've got a 45-degree angle, and I'll say this here is H, and we know this rod goes underneath the water some distance, I'm not quite sure what. And so this is the value x that I was just talking about that I want to find. So this is my curiosity. What might be handy here is if I actually found this length here, and this be x, whereas I know the whole of this is 2h. So it should be fairly obvious that if I'm looking for x, well, x is equal to, well, the whole of 2h minus that length L. So now finding that length L will be kind of crucial. So this L is the hypotenuse of this triangle, this 45-degree triangle, and this h is the adjacent side, not that it matters in a 45-degree angle. So cos 45 is equal to h over L. Rearrange that and you get L is equal to h over cos 45. So that's root 2 over 2. So, and we're dividing it, so it's equal, L is equal to 2h over root 2. Okay, so that's what L is. That's great. We're looking for x. We want to know this length x because that's one of our volumes. So x is equal to 2h minus L. So that's equal to 2h minus 2h over root 2. So I can gather terms here. There's h in both, so I just, and there's a 2h in both, so 2 times 1 minus 1 over root 2. Now, that's the x distance, that's okay. We'll use that in a minute, the length of this x. The other one I want now is the distance from here to here. So this bit is x over, so this section here, I'm looking for this distance, this perpendicular distance in. So in truth I'm looking for the distance from here to here. So this here is x over 2, and this here is what we just said was L. So now I'm going to say the perpendicular distance to the buoyancy is equal to L plus x over 2. So L being this distance that the rod was above the water, and x being the distance submerged in the water, but I don't need all that, I just need this x over 2. So L we said was 2h over root 2, and we said x was 2 minus root 2h, and that's all now over 2. Take the h's out and go 2 over root 2 plus 2 minus root 2 all over 2. So now I've got this whole distance is equal to 2 plus root 2 over 2h. Okay, so now I've got my distances. I've nearly got it all figured out. So if I go for the moments turning clockwise, I've just said it was weight. This is the weight side. Weight is the density of the object. That's S. It's 1,000 S. Buoyancy of the water is 1,000 kilograms. So I'm just going to make that 1. I'm going to make that S and make that S. So this is S over here. Times 1, which I'm not even going to write it. The volume of the object is pi r squared h, or pi r squared times the length. In this case, it's pi r squared times 2h. There's a pi r squared in this case because the volume of the liquid displaced is also pi r squared, but this time it's x. So I'm not going to put pi r squared down on both sides. I could, but I'm cancelling both. I'm just comparing the lengths. So that's 2h. S times 2h. Times g. G is on both sides. I'm not going to write that in either. times the distance. So that is h sine 45. This will also be sine 45, so I don't need to write in that either. So it's just h here. And that's equal to the buoyancy. The buoyancy is the density of the liquid 1 times the volume of the liquid. Yeah, the volume of the liquid is pi r squared times the length. L plus x over 2. So again, if I'm just comparing the length, I'm just going to compare the length here. So it's 2 plus root 2 over 2h. And that's the moment, that's the distance. Whoops. Times the specific gravity times the volume. So the volume of this is actually 2 minus root 2 also by h. And so that's this. You can divide both. You can divide the h's across by the whole lot. So now I'm saying that 2s is equal to root 2. Sorry, 2 plus root 2 over 2, which is what I'm times 2 minus root 2. Is 1. 2s equal to 1. S is equal to 0.5.